My name is John. I'm a researcher now at CAMH, working in neuroimaging. I did a master's here at U of T in computer science. I don't currently use databases for any of the work that I do now, but in some of the work in industry and whatnot, I've used a lot of databases. My plan today was to show you to do a quick tour of the software carpentry lesson on databases, so you at least have an idea of what roughly crudely you can do with a database, and then in the last 10 minutes or so just have a discussion with you guys about what data you have, how you might use it, if the database is even appropriate for that. The software carpentry lectures are supposed to take about 3 hours to do this lesson, so we're going to do 3 hours in 30 minutes or something like that, so strap in. So everyone has Sql Manager or SQLite installed on their command line. There's no one that doesn't have that. Okay. You can go to the software carpentry website. It's just software-carpentry.org/lessons, and then you can go down to using databases in SQL. From there, there's just a link to a sample database to use. So that's the one we're going to play with today. You can follow along if you want, or just watch. So if you're using SQLite Manager or SQL Manager, you just start it from the Tools menu from Firefox. It's a bit weird. But you can kind of see that there. Just raise your hand. Who's using SQL Manager? You guys, and who's using the command line? Yeah, on Firefox, and you're using command line. Okay. That's totally fine. I'm going to try and gauge for both of you. It's both basically the same thing. So when you start SQLite Manager, you open the database first. You connect. They call it connecting to the database. You have to change this little drop-down if you've downloaded the database from the software carpentry website, because it's looking for files that end in .sqlite, but it ends in .db. So you can just find it that way. Click open. That was the little open button. If you're connecting from the command line, I'll just show you that too. So if you're connecting from the command line, you just type SQLite3 and then the name of the database. That's you connecting. If you're connecting from the command line, a few little helpful things. You can give SQLite some configuration commands so the display looks better. So you type mode column. This is all on the software carpentry website, by the way. But type mode column and then header on to just get a nicer display when we do things. Okay. Anyone not connected to their database from SQLite Manager? You're not? No.
What was
this pop up here? Yeah, from Firefox, you just go to the Tools menu and it should be there. Is it?
Yeah.
It is. Okay, good. And then from there, you click the open folder, and then when you open it, you have to change this little drop down to say all files, so you can actually see the file that you downloaded. Okay. So in this little display, SQLite Manager is just a way that we're going to interact with the database. It's convenient because it's easy to install in Firefox. It's not necessarily the way you're going to be using it, but this is just for demonstration. So under the tables drop down here, it tells you that there are tables. You should see all these 4 tables in the database. So if I back up and just tell you generally, a database is for storing tables of data. A table is like a spreadsheet, exactly like a spreadsheet, although you can't put calculations in the spreadsheet, you just store data itself. So each one of these tables, you can click on it and see some info. I would go to the Browse and Search tab because it shows you kind of a more interesting display of the data, but this is kind of like what a spreadsheet view of your data is. So it's got columns and then rows in there with data in them. You're seeing that? So this is the person table. I've gone to the browse and search. If you're on the command line, you can just type tables to see the list of tables. And then I'll show you in a moment how you can get a view of the data. We'll get there. So in database terminology, these are columns, and each row is called a record. Okay, so the cool part comes when you actually you write queries. You kind of write code to extract data from the database. So I'm going to give you a quick tour of all the different kind of commands you can do. Well, just an overview of the commands you can do with SQL to extract your data from your database. Okay, so you click the execute SQL tab, and then here's where you write your commands. So the first command we're going to write is select star from person. So there's the person table. You just write select star from person. You can type this in from the command line exactly the same way as we're doing here. And then you hit run SQL. So it returns you, the star is saying it's a wildcard to say, give me all the columns from the table person. Is anyone not getting this? You're all, okay, good. So, okay, so we've written a select statement, which says grab those columns. You can actually specify the columns you want specifically. So you could say ident and personal to grab just those two columns, or personal and family. You can specify which columns you want to grab from the table. If you're doing this in R, you would use, like what, you'd use subset, I think you can use to grab columns, or dplyr has a yeah, if you wanted multiple columns, I guess you'd have to give it like square brackets and give it a vector of all the column names. Yeah, this is basically doing that from your table. And you can list the columns, and you can list columns twice if you want to. It doesn't matter. So this is saying select these columns from this table. Typically, we might write, I'm not going to do it for this because it takes a bit too long to type, but you often see people write the kind of keywords in capitals and then everything else in lowercase. SQLite doesn't care about case. Some database managers actually give it, actually care about case. Okay, so that's select. So let's write another one. So if in the survey table, you can go there and see it. You can see that there's a bunch of, this is supposed to represent like measurements from devices or taken by people. So this is like the person who's done the measurement. This is the kind of measurement, and there's the reading. So if you wanted to write a statement to just grab all of the readings from that table, from the survey table, you would do what? Just someone call it out. What would the statement be? I just want the reading column from survey. Right? So let's just select that one column. You can get, in this case, okay, so I'm going to, quant tells us the kinds of measurements that are being done. If you want to get a unique list of those, you can just use the distinct keyword. So select distinct quant. So this will take all of those that were returned and just find the unique set and return them. So I'm not good with my capitals here. I'm going to stop doing that, but this is the idea. This is a distinct keyword that says take a distinct set from the columns that you've returned. So if I added reading, well, that's not going to work. I'm going to add taken. So this is maybe person. Yeah, that's nice. Okay, so this says, this is giving me the distinct set of pairs from that table. You can also order or sort your results that you return. So you just say, select your columns from your table, and then you say order by, and then you just give it a list of things that you wanted to order by. So this is now sorting that list by that column. And you can order by columns that you're oh, you can order, I guess, like this is, I guess, doing it in ascending order, and then you can also change it to descending order, just giving this keyword. So you can see how you would do this in R or Python or whatnot, but it would be multiple commands, right? You would select your data, you'd load your data, you'd grab just the columns you want, and then you'd order and all that sort of stuff. So, but with SQL, you kind of just compact it into one statement. Okay, you can also give conditions. So you can say select from select star, which is all columns from the visited table. So we can see those here. But I can say where the site is equal to dr-1. So this is just restricting, I just want those records. So this is like a subset command with a condition. And you can do all the regular things you would want to do with conditions. You can give like booleans and whatnot, so you can combine a bunch of things. So you could say, and ident equals 619. You can also do things where you kind of match regular expressions or you match patterns. So you can say, select all the columns from the visited table where the site column is like, and then this kind of nasty syntax, but you say a pattern, you can use the % sign as the wildcard. So this is matching all the sites that start with dr. Yeah. Some database engines are and some aren't, so it's best to look it up. I think this will work. Yeah, it happily did that. Yeah. So this is the thing about SQL. There's a couple different standards for it, and some database engines respect some, and then they have their own unique set of like other extensions to the language. So there's no one SQL that you can just learn and apply everywhere. So you have to kind of tweak it to the database engine that you're using. But the stuff I'm showing you now pretty much works across the board. So, okay, so this is matching a pattern against a column. So you're just returning records that match that pattern. You can do things like, it's got this date column, and you can say, SQLite makes date handling fairly nice, so you can just actually say less than and give it a string that matches the date, and it interprets that as a date and does the right thing. It's a bit magical, but there are rules to it. So you can say things like that as your conditions. You can also give sets, so you can say, take from the survey table. So this is what the survey table looks like again. And if I wanted to look for rows only by certain people, I could say where person is equal to this guy and, or person is equal to this guy. That would be fine. That would give me just those records. Sort of a more succinct way of doing it is saying like person in and then giving it a set. So I can say dire and. So you can use this in syntax to give it a list of things to match. What just went wrong there? Is it, did I get it wrong? Is it PB? Yeah, okay, there we go. Good. Nice. Any questions so far? But it's pretty straightforward stuff, right? Yeah, okay. The other thing you can do is not just select columns from your table, but you can do sort of math with them. So you can say, here's the readings column from the survey. So that's just return the readings, but you could also do some math. So you could say, I want to multiply it by some amount. So you can give it all sorts of expressions on the data that you're returning. There's a fairly expressive language. I think you can, yeah, you can round, and you can round by certain decimal places, I think. Anyway, so you can do a bunch of different operations on your data as it's being returned. And of course, everything else we've done applies. So you can restrict, you can do where clauses. You can do where clauses that match survey. Yeah, so you can do where clauses that match columns that you're not returning. So you can say like where the person equals PB in this case. Just because you're not returning a column doesn't mean you can't do a condition on it. And okay, one little hitch that you'll run into is if I look at everything from the visited table, there's this null value. So this is just missing data. Like in R, it's an NA. In SQLite, it's referred to as null. Like it actually gives this sort of value. So you might say, like, how do I select the missing data? And if you would naively just say, like, oh, dated equals null. You get nothing back. And this is because any expression involving null equals null doesn't equal true or false. So the where clause just actually doesn't match anything. So to match nulls, you have to use the is operator. The is, you'll actually get your null. This is kind of a problem when you have missing data and you're not anticipating that you have missing data, because if you say, well, if the date was less than 1930, you will get those two rows. And then if you said, well, what if I get all the ones that are greater than and equal to that date, you would expect to get in one of those two sets the null, but you don't, because the null, when it's being matched against that where clause, just never equals true or false. It always equals null, and so that where clause never actually returns that row. So that's kind of gotcha if you have missing data that you won't know about unless you sort of do a couple checks. Some checks you can do for that, though, are you can count. So one of the things you can do, one of the expressions you can give is just to count all of your records. So this gives me a quick count of all of the records that I'm matching, and if you add those where clauses in afterwards, you can use that to kind of figure out if you're missing data. So this is a quick way to just count how many rows are being returned.
Does it distinguish between missing data and null data? Like if there's things that just shouldn't be filled out versus things that are missing it?
Okay, so a null is just a special value that the database knows is different from a string, from an integer, from a date, from everything else. It's a completely separate data type. So you can use it to indicate missing data. You could use some other value if you wanted to, but it's traditionally the way you represent missing data, to stick a null in there. But it's up to you. So you could use some other special value, but you'd have to manage that yourself. Does that make sense? Yeah. It's like an NA in R. It just doesn't behave the same way as NAs in R. It's a bit nastier. Okay. And okay, so we did count, which is kind of like, if you can, I'm going to call this an aggregation. It takes all the rows that are being returned by the rest of the where statement and whatnot, and then aggregates it together into just a count. But you can do, so I could have put a column in here. For count, it doesn't matter. It's just counting the rows. Oh, right, because I want this table survey. So the fact that I used the star in this case doesn't matter. It's just counting the number of things that returned in that column. But for other aggregations, so if I wanted to do like an average, in this case, it's AVG, and so that's just calculating the average over all the rows that were returned. So if I stuck a where clause on there, then the average would be just taken over the rows that were returned after filtering. There's average, max, sum. There's a bunch of other ones here. And right, okay. You might want to, so let's look at the survey table again. So you might want to say, what's the average reading taken by each person? So in that case, you can take the average reading But that's giving you, oh, what did I do wrong? Oh yeah, in some database engines it's average and this one it's AVG. Okay, so if I wanted to get the average for each person, I could write multiple queries, right? Average from survey where, person equals whatever, where person equals whatever, and just loop through them all. Or you can use the group by clause. So I can select, in this case, the two columns, the person and the average, and group by the person. And so now I'm getting an average per unique thing in the person column. I can stick in wheres as well. So I can say like where person in and give it a bunch of people. So I can combine. Sometimes people write these out in multiple lines, so that it's a bit neater here. So this statement is saying first filter the whole survey table by those people, and then group by those each person that's returned, and return the average for that person.
So it always does things sequentially.
It doesn't do them sequentially, so you can't put the group by first and then the where. It always, there's a certain order of operations, so it filters first, then it groups, and then it selects those columns. So that's a really good question, because you have to know that it's doing it in that order, or else you'll get, just to know that's how it's calculating those results. Okay. Okay, so far we've just done operations on one table, but the real sort of power, I guess, in the databases world is that you can join tables together and start selecting results across multiple tables. So in our case, we have, if we just look at the site table, we have this name and visited. Yeah, so we have this site that shows up in the visited table and in the site. This column, called site, that shows up in the visited table and shows up in the site table as name. So we actually have a link between these two tables. We have in the site table information about each of the sites. So there's the name of the site and then the location of it. And under the visited table, we have a site column that says, when did we visit that particular site and who was it that visited that? And this is some identifier for a person, I think. So we could say, well, I want all the information about all of the sites, their location, and when we visited them. So I want to merge those two tables together. Does that make sense? What we're trying to do, we're trying to get, because this site is sort of a key into the other table, we want to merge on that key and say, just like you would with R, you could use the merge to merge two data frames together. This is the equivalent we want to do here, is merge these two tables together.
Given the fact that you have multiple entries per site.
Yeah, so ideally what we would want is a lat long for each of the sites. So we want like a repeated, we want each one of these rows to show up, but instead there'd also be a lat long column that would show the lat long for each of those sites. That's what we want, right? I mean, that's what I'm telling you we want. So the question is how we get that. Okay. So you use the join operator. So you say, select from the visited table and join with the site table. If you just do that, it does something wacky because you haven't told it that there's this link between these two tables. You haven't told it that the site table in one matches the name, the site column in one matches the name column in the other. So what it does is just takes, for every record in the visited table, it puts all of the records in the site table. So you've got, in this case, each, it's a bit confusing here, the way that it's laid out, but you'll have to trust me on this. It's just done like a cross product of those two tables because it doesn't know that there's that link. We have to tell it that there's the link between those tables. So you say select from your table, join to the other table, and then you give it the on clause, and you say where visited dot site equals site dot main. So this is like a where clause where we're just saying this entry here must match this entry here. We only want those records. We don't want the ones where the sites don't match in that cross product, or just you're telling it.
So before you had like the number of lines and what's the product, like you would have a product with the two tables?
You would have a cross product, yeah. For every row in one table, you have it matched with every row in the other table. So you have to tell it which columns are ones that actually match. This is the same as the merge function in R, if you're familiar with it, where you have to say by like .x equals the column name. You tell it what you want it to merge on. So when you run that, it only returns the ones that actually match. So this is joining two tables. And you can join like multiple tables. If they each kind of have links to each other, you can pull them all together with a join. So you can just say join site, and then you can say join the next table, and you can keep writing your joins, and then you write a series of ons to match them all together. And then you can also here do everything else that we've been talking about. So you can put wheres and groups and all that kind of stuff. So you can do everything you can do with a single table with a join. Conceptually, what it's doing is it makes a temporary table with the join and then runs your other operations on them. So because we're running a bit low on time, I'm going to not type out the complicated query, but you have to trust me that you can join multiple tables together. And then you can do your groups and all that kind of stuff. So the last little thing, or last little bit that I want to talk about was, so far we've just been selecting from the database, but you can also write SQL to insert values or update values or delete values on a table as well. So it's very sort of natural if you just want to insert into the site table the values ER1. We'll just give it some lat longs. So you're saying insert into the table, and then you give it the values, and those values match the columns that you want to insert. Match the columns in the table in the same order. And that just runs, and now so there's my row that I added in there. So this inserted a new row into the table, and you could keep running this if you wanted. And great. I just ran it a handful of times, and now I've got all those rows in there. So there's nothing to stop you from adding data. You can actually add restrictions, and you can tell the database engine that certain columns should be unique and all that kind of stuff. So it will kind of enforce referential integrity, it's called. So you can actually tell it, these two tables are joined on this field, and so don't allow me to insert something without inserting something else there that matches. I mean, there's all sorts of other levels of complexity you can add here, but basic idea is that you can insert into a table just using an SQL statement. You can set default values for columns, so you don't have to insert values for every column. That's a bit more complicated, but you can actually list the columns you want to insert values for if you don't want to insert them for everything. Anyways, and then if you want to update an existing row, you just use update and then the name of the table that you want to update, and then you set whatever value. So you set like the lat equal to 50, oops, sorry, not in quotes, 50, and the long is equal to 100, and then you set a condition where name equals MSK. So this will update those two columns where this condition matches. So it basically does a select first, finds the rows that match those conditions, and then updates the columns there. So you better only match one row in this case. If you didn't put the where clause, you would update all of the lat longs across all of them.
Is there a way to undo?
There's no way to undo. Yeah. It's not entirely true, depending on the database engine you're using, but not in SQLite. There's no way to undo. It's kind of like RM on the command line, where you can just destroy all of your data. Yeah, and there's no version control for databases that are built right into the database, so you can't git checkout to get back your stuff. But you
How
can
do you do that in real life?
you can commit your whole database. It's just in SQLite, it's just a file. So you can do that. You can also export from your database to like all of the insert commands that would have taken you to rebuild the database, and you can version control that, which is nicer because it's text, so you can kind of diff between versions. But yeah, versioning databases is not a particularly fun thing to do. So it's typically easier to, if you're going to version your data, version it in some other form, then import into the database, do your work, and then extract it from the database. We'll talk about that a bit more, but I just want to show you that you can also delete rows by just saying delete from table name, where, and give it a condition. If you don't give it a condition, just delete everything. Yeah, no undo button. But you can see how I think the syntax is fairly memorable. It's fairly straightforward. Like, it sort of feels like natural language, which is one of the advantages, I think, to using a database. Is if you could see how the stuff that we were just doing, the selects and the orders and the groups and all that kind of stuff, would take you multiple lines of code. But you could just write it as one select statement. So I would say that's like the one reason why you might use the database, to simplify your code. The other reason you might want to use it is if your data is larger than what can fit in RAM. Database engine is really good at just saying, if you're saying select only those rows that match this condition, I couldn't fit the whole table in memory in order to subset that, but the database engine can scan through that and collect all the rows that match and only return you that chunk, including you can just grab those columns that you want. So you can really kind of narrow in on the data you want, even if it's gigabytes or terabytes on disk. And that's really, SQLite is not necessarily like a powerful database engine, but some of the more powerful ones can handle just gobs of data and can work very quickly on very complicated queries. I haven't shown you complicated queries, but you can do all sorts of nesting queries. So you can use one query's return results and then feed it into another one. So you can kind of have these pipelines of queries. You can do all sorts of wacky stuff. And the database engine makes a nice plan for how to do that and executes it without loading everything in memory. So if you have a lot of data that doesn't fit in memory, you can use a database. If you want to simplify your code, if you have data that's like being continuously collected from some device, it's sort of an online thing where you're just collecting, you could just append that to a row in a CSV, or you could use it like insert statements. You can connect to a database from Python and from R and whatnot, and so you can keep just sending it insert statements to add to your table, and you've got a record, and it's you can have all the features of being able to check data types and all that kind of good stuff. And then the other reason I would say is if you have data that's structured similarly to how we were talking, where you have multiple tables and those tables are related in some way, you could load them into memory and use your merges and subset from R, or do the equivalent in Python. But it's probably just easier to use a database because you just write the SQL statement and you're done. So that's your like really, that was 3 hours of software carpentry boiled into 30 minutes. I thought maybe we could just talk about the data you have and whether it would work or how you might use it in a database, or whether it just maybe is not appropriate for a database. So based on what I've talked about, does anyone think like, oh yeah, this I could see using this for my data? Yeah.
I have a question. So sometimes if you have kind of more complicated data sets or relations, is there a rule for designing your database where you can?
Yeah, there's lots of sort of database architecture. I don't want to call them rules, but sort of hints around how to do it. And most of it involves, one, thinking about what kind of queries you're going to run, because if you have a bunch of data that's broken up into multiple tables and you have to keep running joins, that can be expensive. So sometimes you want to not split up your data into multiple tables, if that makes sense. But sometimes you actually do want to, you can remove a lot of redundancy if rather than having a column or a column with repeated values, you can just break it off into a separate like lookup table that you just join back in. You can actually really cut down on the amount of data you are storing. So there are all these, there's actually a fairly rigorous, there's a whole database theory, and they talk about different normal forms that you can break your database into. that give you some idea of how to like reduce the redundancy in your data.
Designing.
Yeah, it's a fairly involved, like you can go down this whole rabbit hole where you just, you know, spend your life trying to design this. And it actually really matters. Like, so I worked on a project with Blue Cross, which is like an insurance company in Michigan. And they had this, like, they wanted to run, it's kind of a boring thing that they're trying to do, whatever. They're trying to run their finances to figure out, like, are we in debt or not, sort of thing this month? Did we make money or not? And they have a whole database which stores, they use day-to-day to record, like, okay, this person's plan got set up and it runs from this date to this date, and we charge them this much money and blah, blah, blah. But when they went to go run their like monthly or daily queries, they had to do all these joins and it was just taking forever. So the company I worked for was required to build a database that was in a different form that had all the same data. They would load the data in so the queries would run fast. And so it took, you know, some architect to decide, okay, this is the way we're going to design it. So hopefully you're not in that situation. You don't have that much data that it should matter. But if you do, you really can go down a hole trying to design. Yeah.
So I'm in a situation where the data is like tons of relations.
Yeah.
So I'm needing to reject it to have it be flat.
Right.
So that's why I think it makes sense.
So you have it right now in flat files and lots of redundancy, or?
Yeah, I mean, mostly it doesn't even exist in flat files. I just have the scripts to make it.
Okay.
Have you like made it?
So you make the data, and then are you doing kind of, you can see how you could use these queries to pull just the chunks you want out of it. Are you doing any of that now in R or no?
No.
Okay.
So far it's like step one to this step two.
Right.
It's just like creating a database, and then querying can be like what a user would want to do. So I've gone there.
Oh yeah, because this is an open source. Yeah. You see, that's perfect, because then you can let users, I mean, in a controlled way, write their own kind of query.
Like, I think if it was flat, it would be too, well, flat would be fine, but if you structure it with the relations, then people can do whatever queries they want. And it's like, kind of,
Yeah.
so,
Yeah, you can also give people like a nice organized way of writing their queries, like a web interface that says, okay, select these columns from these tables, and you can automatically join tables together. Like you can, if you write their relationships into the database itself. So there's some things you can do that way. That sounds like a good use case for a database then. Yeah.
What's good about that makes it a good use case?
Well, it sounds like there's multiple tables of data that have relationships between them. The tables have relationships between them, like they're shared columns that match from one to another. So you could merge all of that together into one ginormous table that you feed people, or you could break it up into multiple tables and let them just pick the pieces they want together. So do you also have a lot of data? Like, is there like gigabytes, terabytes, that kind of gigabytes? Okay. So, I mean, that really matters if you're trying to, like, if you're just trying to do it in R and you load up 8 gigabytes of data into R, and then R adds on not just 8 gigabytes, but it's trying to represent all that in memory. So it adds another, you know, X amount to that. All of a sudden you have no memory to do anything else in your machine. So a database can keep all that on disk, but you can still do all the work that you normally do to query and subset and merge and all that. So, yeah. Does that make sense? Yeah.
I've got a question that's sort of science related, but
Yeah.
I'm interested in representing the control of the data. So it's sort of like the example you gave.
Yeah.
But so you have the budget, and the issue is that it doesn't stay the same over years.
Yeah.
So it's like, it would be easy if it did. Let's
Yeah.
say, one example, say 2010 is like parks and forestry, but in 2011 it was parks and forestry.
Yeah.
But say I want to do a graph and compare those over time, and just say, like, well, suppose that they're the same.
Yeah.
Because I know that like parks and forestry became parks and forestry. Like, how would that? So right now, I say I have a different CSV or CSV is different here as well. I don't know how to match those up.
Yeah, that's a tough problem, because you have, it's like the database design is different from year to year.
Yeah.
Are you liberating this data from like PDFs or?
Yeah.
Yeah, okay. Are you, okay, I think I know something about this. Okay.
Well, it's with like Civic Tech.
Yeah, okay. Yeah, so there's no good answer to that, but if you can upfront design a schema, like an organization for your tables, where you could load the data in and say, okay, year one is Parks and Rec, but I'm gonna, when I load it in, split it into the two tables. And then year two, it's already split, but I'll load it into those same tables. That would be maybe one approach. So you kind of have to think up front, but you know, the year later when they change things again, you're kind of hooped.
So we like sort of been doing it is going backwards. So say you start this year, you have these codes,
yeah,
and you go back and you just say like, oh, Parks and Forestry rolls into, right, or Parks and Forestry both roll into Parks and Forestry or something like that. I'm still like cleaning up a lot of the stuff. So it's like I'm just trying to think like I have no idea how I'm going to do this.
That's, I mean, the database is your tool to make it happen, but what you decide to make happen is, in your case, a particularly hard question because you want to get the right organization where you can load all that data in over the years. And like kind of you're unifying the data, that's tough, yeah. Like each year is going to have to be handled separately. You're going to write a custom code to say, yeah, in this case, do that and whatnot. The database could hold all that data when you decide of a good organization that you want that will manage all the years, but you'd have to decide that up front, how you're going to break it up. That's not a very satisfying answer, but
no, yeah. I know I need to figure stuff out.
You could, if you want to talk about it and like get into the gory details, then yeah, I'm happy to do that.
So then you can change the structure on the fly and
improve that. I don't know.
Okay, so no SQL. Has anyone heard of this? Other than you guys? No. No SQL.
I've like heard that.
You've heard the term.
Word.
Yeah. It's basically like, let's put stuff into a database without having tables defined for us already. It boils down to, I mean, crudely just key pairs, like this equals that sort of thing. And so it's like just shoving a dictionary into, or just key pairs into a data. So yeah, you don't have to worry about your schema changing over time, but now your code gets that much more complex as you're trying to figure out like, okay, I've just got this key pair blob. How do I pull it into a form that makes any sense? So it's good for some applications. The software carpentry sort of perspective on that is, it's not clear which sort of technology is winning right now. So, and it's also, there's tons of legacy data that's already in databases. SQL is really nice for using that kind of data. Learn it at least before you venture off into the no SQL world. It's not necessarily going to help you in the long run. It may help you immediately just say, I dumped it all in the database, but then when you try and use it, you're kind of hooped. What's that?
How do you make a database? How do you make the
Yeah, okay, we didn't talk about that. There is SQL that you can write where you can say like create table and then you can give it columns. I don't know the syntax offhand, but it's something like this. And then you can say like column, actually I don't know it offhand, but anyways, you can say the column, the data type, and the name. And so you can give it a series of.
And you have to like insert every value manually.
Yeah, okay, so you can, yeah, good question. Okay, so this is creating a table and its structure. Getting the data in, there's actually some really nice ways to do that. SQLite has built in a command called load or something. I don't know it offhand, but there is some, yeah, load. No? Import. So you can import like a CSV file and it'll create the table, I think create the table, or at least load it into a table that already exists. Python, R, they all have libraries where you can just slurp data in. You can just dump the data frame into a table. So that's how you get your data in. Yeah. Or you can, like I said, if it's an online thing, you can just write code to like receive from whatever device and just insert as stuff is coming in.
When you import, is it generally CSVs or there's other ways or other things you can import?
Well, like in Python or R bindings for this, you can just, whatever data you can get into a structure that the bindings can handle as an insert, like a dictionary or whatever, a list of dictionaries or whatever. Yeah, so from SQLite, from the command line thing, it actually has a import this CSV, but I don't think it handles any other data type. I might be wrong about that. Yeah, something else I didn't talk about, like, I mean, this is more technical, but you can set indices, you can set certain columns to say like, I'm always going to do like wheres on these columns. Like I'm always going to filter on this column. So build a little index of the values in that column so that I can do quick kind of searches. So you can kind of optimize your queries to say, I'm always going to be searching on that rather than going through every row. I've already got an index that tells me for this value, here's where all the rows are. So you can do all sorts of, just to say that you can do all sorts of optimizations to make things run a lot faster once you have your data loaded in. But that's a more sort of technical side to it. The other, I didn't show this, but the other thing you can do that's handy if you're starting is if you're looking everything from a table, you can limit 10. So this takes the top 10 results. So it's a good way to get just a kind of view on what's in the table if you just want to sample. I just find that's a handy query.
For sorting things, is
Yeah.
there any particular way that would optimize?
You can create indices on tables.
Indices?
Yeah. Yeah.
So basically, any row that gets deleted, the indices still like keep going. It's like 0, 1, 3.
No,
or is it always going to be 0, 1?
No, an index is more. It's like it's
Unique ID.
It's not even that. It's a table. I'm going to call it a table. It's a lookup table that the database builds just for itself. You don't get access to it, but it's kind of compiled a list of the data that's in that column and figured out where the different values are, and it's sort of in this highly optimized form. Yeah, but it's nothing you have access to. It's just a hint to the database engine. Yeah, yeah, exactly. I think we're sort of out of time, but if anyone, right?
I'll start the stream then.